Hi, Steve Denenberg here, with the third in our series of videos on the physics of springs and simple harmonic motion. We're going to discuss one more simple harmonic motion formula that is on the page of formulas that you receive at the beginning of the AP exam. If we go back to the page of formulas for the AP test, and we zoom in, we see this formula right here. X equals a cosine 2 pi ft. That f is frequency. What is that all about? Let's figure out where that equation came from. I want you to understand, but not memorize, the following derivation. But just following along will reinforce your understanding of frequency and period and angular speed. Here we have two charts of y equals cosine of x of some sort. Ignore for the time the units along the x-axis. The cosine, as we know, varies between a maximum of 1 and a minimum of -1. In this chart, the cosine is varying between 1.8 and a minimum of -1.8. And that's just because this chart is y equals 1.8 times the cosine of x. So here, the 1.8 is the amplitude of the motion. So we say y equals amplitude cosine x. And this is like our amplitude from pulling a spring and letting it go back and forth. Now, in these two charts, x-axis is time. And if you want to increase the frequency of oscillation of the cosine curve, you say y equals a times the cosine of something times the time. If the factor in front of the time is large, you can imagine that you don't need much time to have this move from 0 to 2 pi and have the cosine complete one cycle. If omega here is equal to 1, we have y equals the amplitude times the cosine of time. And at time equals 0, the cosine will be 1, and time has to move from 0 to 2 pi seconds for the cosine to get down and all the way back up to 1 again. On the other hand, if omega in our equation up here equals 2 pi, then our equation is y equals a times cosine of 2 pi times time. And still, at time equals 0, the cosine is 1. But when the time goes from 0 to 1, this angle, and cosine operates on an angle, goes from 0 to 2 pi. So the cosine of 2 pi times time gets back here as time goes from 0 to 1 because of this factor. In the previous example, omega was 1, so this is time 0, and it took 2 pi seconds for the cosine of 2 pi to get back to 1. So this is y equals amplitude times cosine of omega times time. And in this situation right here, omega is 2 pi. Well, let's try it again. We're having fun. Let's do it again. Let's say omega equals 4 pi. Now we have y equals amplitude times cosine of 4 pi times time. At time equals 0, this angle will be 0, and the cosine will be 1. How long before we get back to a cosine of 1? Well, we have to get up to an angle of 2 pi, before we complete our one cycle and get back to a cosine of 1 again. And for this to be 2 pi, time has to equal 1/2. And we've made one cycle in a time of 1/2. Sounds like we have twice the frequency. Well, let's take a look at these charts. Here's a cosine chart with an amplitude of 1.8, and from a cosine of 1, an angle of 0, it takes 1 second to get back where we were. After 1 second, the angle is 2 pi, so our omega is 2 pi. And our equation here is y equals a cosine 2 pi t. Now here, it only takes half of a second for the cosine to do one complete cycle. And that's what we had here. If omega is 4 pi, we have y equals a cosine of 4 pi t. And it takes 1/2 second to complete one cycle. And so the frequency is 2. And sure enough, we have 2 cycles per second. And I always say that if something is fun, we should keep doing it. So let's do it again. This cosine chart has a frequency of 3. There are 3 cycles per second. 1 second, 2 seconds, 3 seconds. In 1 second, the cosine gets from 0 to 2 pi to 4 pi to 6 pi. 6 pi in 1 second. Well, if omega is 6 pi, we're looking at the cosine of 6 pi times t. And sure enough, in 1/3 of a second, this will be 2 pi, and we're back to a cosine of 1. So that's the equation of this chart. And our frequency equals 3 per second. Now, a long time ago, we discussed that since a frequency is one entire cycle, and one entire cycle is an angle moving through 2 pi, that the angular speed of this chart equals 2 pi times the frequency. And since the equation for a cosine of varying frequencies is y equals a cosine omega times t, with a frequency of 3 per second being equivalent to an omega of 6 pi, we can also write this y equals a cosine of 2 pi times the frequency times the time. Because 2 pi times the frequency is our omega. In this example just above, we saw that the frequency was 3, and the omega in our equation is 6 pi. Now, if we want a frequency that's higher, let's say we want our cosine to go up and down 11 times each second. That's a frequency of 11. And we can just write down our equation. Y equals a times the cosine of 2 pi times the frequency of 11 times t. And now let's go back and assume that we are looking at this chart edge on as a bead on this curve follows time. It's going to describe the simple harmonic motion of a mass on a spring going back and forth. As with time it comes down, seems to pause here, comes back up, seems to pause there, maximum velocity here, back down, and back up. So if we are thinking of watching simple harmonic motion of a mass on a spring oscillating back and forth with a certain amplitude and a certain frequency, which is full extension to extension or compression to compression cycles per second, and we say that the equilibrium position is at 0, the mass is going to move out toward positive A, and then it's going to move back toward negative A, and it's going to move back out toward positive A. And now we can write an equation that we know exactly where it's going to be at any point in time. We can say that x equals A times the cosine of 2 pi times the frequency of motion times the time. So this is actually x of t. X at a certain time equals this. And that is where that equation on the formula page for the AP Physics tests come from. Can we visualize that function, that motion? Sure. Desmos to the rescue. So here's a visual representation of our equation, x equals a cosine 2 pi times frequency times time, a mass oscillating on a spring. The amplitude A is 3. The mass goes to +3 and -3 at its extremes of motion. Here the frequency is 1/2. 1/2 full cycle per second, or 1 cycle every 2 seconds, or half a cycle per second. You can see that. Count the seconds. 1, 2, 1, 2, 1, 2. If we increase the frequency to 1, we get 1 full cycle per second. One, 2, 3, 4, 5, 6. By the way, I'll put a link to this Desmos chart in the description. Let's increase the frequency to 2 full cycles per second. One, 2, 3. Let's count every other one. 1, 3, 5, 7. Now let's go back to a slower situation, a lesser frequency, so we can notice a couple things about this motion. Here our frequency is 1/2 again. The Desmos chart is simply following our equation, which accurately describes the simple harmonic motion. At the extremes of amplitude, the velocity of the mass drops to 0. That makes sense. The total energy of the system is constant. The total energy. When the spring is fully compressed or fully extended, all the energy is tied up in the potential energy of the spring, and there is no kinetic energy. I didn't mention it before, but the spring doesn't need to be compressed to absorb work and store potential energy. You can put potential energy into a spring by pulling it into extension as well. You are applying the same force over the same distance, and when you let go, the potential energy you created with your work is converted into kinetic energy. So at the extremes, the potential energy is maximum and the kinetic energy is zero. Then, when the spring is at its equilibrium position in the middle, at x equals 0, at its resting length, the spring is neither compressed nor expanded, so the spring holds no potential energy, and all of the energy in the system is now kinetic energy. So the mass is fastest as it passes 0 in the middle of its range of motion. Pretty cool, huh? Okay, thank you for tolerating me through this series of videos. I hope you understand springs better now. Your feedback is always appreciated. In coming videos, I intend to present and solve several sample problems related to springs and simple harmonic motion. Thank you.